So we'll look at some of the principles, some of the assumptions, and then we look at how they come up with the stress strain and the stress block diagrams in the Eurocodes, so that you can then design your beams. So you'll find that with concrete, the top half above the neutral axis, so that's our NA, which is usually like some XX. Your concrete is normally in compression. Then you'll find that the steel, which is predominantly in the bottom, that'll be in tension. When we come to design reinforced concrete, we have to try and make sure that the steel is the thing that fails, because it fails slowly, it yields. We don't want the concrete to crack because people will die very quickly. So you'll find that we'll start looking at the force in concrete, and we'll look at the forces in steel. And the force in steel stays the same, because you find that the stress of the steel is 500, though the design stress is 435. So that's kind of set. Then with the concrete, you can then sort of choose which stress of concrete you want to use and the dimensions. And you'll see that the formula is very much built upon the width B, and you've got the depth, which is D, which goes from the top to the reinforcement bars. And like concrete above the neutral axis is considered for compression, so we will use that. But when we come to do the design, you'll find that the concrete below the neutral axis isn't actually considered in the design. Normally, because when a beam bends, you end up getting like a lot of cracks within the bottom half, so they don't rely upon that. And all of the tension's held by the bars. Concrete's got like about 10% sort of tension, but again, it's not considered in the design. So the whole point is that we try and you'll see how we'll try and mess around with this neutral axis location to try and make sure that the steel is going to fail first, or yield first. So some of the assumptions, this is like a 2D diagram of what happens because you've got the steel and the concrete are joined together. The strain will be the same linear throughout. So you would have seen this diagram before, where above we've got the strain epsilon in the concrete, and these are values that you have to pull out of the Eurocode. And at some point at the neutral axis, there's neither compression nor tension, and then that all goes all the way down to the level of the bars, where you've got the strain of the steel. So you've got epsilon, and just like what I've said there, this is just saying that the pink area below the neutral axis is concrete, that we don't consider any tensile strength from the concrete. Page 34 in Eurocode 2 introduces this theory. So if you go to page 34, which is 316, yeah, got page 34 and 35. You should have an image that looks like that on the right hand side. Now in the Eurocode, they don't give you the formula to do concrete design. They give you these images, and then from these images they expect you to write the formula. yourself or work out the formula for your country. And so you'll find that to do design, you will have to go to academic books to interpret the Eurocode. Now, in terms of the formula that I'm going to give you, it's based upon a Thomas Telford course that I went on. You'll find that there are documents by the Concrete Centre. Here's like an example one on beams, which you can print out for free. And you'll see that there's flow charts with some formula in. Now the formula looks slightly different to what I have on mine slides. I've sort of followed one book by Mosley, and you'll find that they're all trying to sort of make a stamp on a way of doing the design. And you'll find that even though the formulas look slightly different, they always come up with the same answer. They've just decided to put certain factors in and decided to multiply out at different times, so that some of the formula look very different. So it's worth printing out these Eurocode, these Eurocode guides by the Concrete Centre. Because one, it gives you the fire tables, so that when you come and do your cover, you've got the actual tables for the fire, and secondly, it gives you the flow chart guidance. So it's based upon these charts, and what you'll find is that when people are approaching the design of concrete beams, there's 3 approaches, and they're here, and they're written in clause 317. You've got the formula derived from the short-term stress strain curves. That's very, very complicated. Nobody is doing that. So, secondly, you've got the design charts on which are based upon option C, which is the stress block option, what we'll be using. What you'll find when you come to industry, you'll be using these flow charts in the stress block, but in order to speed up the process, and you'll see within the Concrete Centre, you've got all of these charts with curves on, and sometimes that speeds up how quickly you can do the design of single reinforced or double reinforced. In terms of what we'll be going through the stress block option. There is only sort of one way, so it'll be based upon the Eurocode, but then different people have interpreted the Eurocode slightly differently and have their own set of formula for designing. You will find that they're all largely the same. I'll show you some examples of what looks different. But yeah, so in Europe you're expected to use Eurocode, and you're expected to use this stress block technique. The only time you would use different is if you went to like America or anywhere else that they use a code outside of. In the UK, we also use the British Standard code, and I'll show you some of the differences. Some of the things are similar, some of the approaches are slightly different, but Eurocode is what we design to now, and so this is what should be the predominant thing that you learn. Oh yes, and yes, by unifying it, it has made it a little bit more complicated, but people will get used to it, and you'll find that that people will specialise in structural design and get used to it. For those who dip in it and come out, and you'll find that you probably won't do a lot of design, because it's faffy.
Why don't you still stick with the US?
Because they know it. They've been doing it for years.
Still less complicated.
I'm sure back then it was complicated, because before that there was a CP something. So there was a CP something code of practice. Then the British standard came in. Some older guys use the CP method to do their initial design, and then when they've got to do the detailed design, they do it in British standard. But if it just so happens that they work for a company that require the Eurocodes to be used, they have to do it in that one also. And there are some differences in between the codes. But yeah, I don't know. If a building went to court, would you be expected to show your accounts, and should they be with the latest codes? The British standards are classed as withdrawn now, but people are still using British standards. Yes. So last week we introduced. First, we look at in order to come up with a formula. There's two things that we have to consider: the concrete and the reinforcement. We'll look at the concrete first, at this stress-strain relationship. So we looked last week at this design of concrete strength is 0.85, which was that alpha CC times by the characteristic strength of the concrete divided by the gamma C, which was the factor of safety. Now, you'll recognise this diagram showing the strength of concrete over a short term, so like 30 days. And the dotted line at the top is how strong concrete actually is. The solid line, when you apply the factors of safety, is 1.5, and that it brings the strength down that we're actually relying upon. So this here is just the same diagram, and in terms of how they make the stress block curve, they rotate the stress strain. So if you've got the neutral axis, and if you've got the maximum compression at the top, so there's a maximum compression at the top, as you come down, by the time you get to the neutral axis, you have zero stress within the block itself. So this is how they're making up the stress block in order to get the formula to do the calcs. So this value here is FCD, so that's the maximum amount of compressive stress in the top. Then you've also got the strain diagram, where you have the maximum amount of strain, compressive strain at the top. You get no strain at the neutral axis, and then you've got the maximum amount of strain in this steel at the bottom. So they're going to combine both of these to get some formula. They call it a simplified stress block. Rather than working with the dimensions of this curve, they take that triangle there and put it there, and they make it into a square block. So that's why they call it the simplified stress block. In terms of the dimensions of that, x is the distance from the top to the neutral axis, and in the UK we take 80%, so you find that lambda in the national annex for the UK is 0.8, and then you've got this eta value, which I'll tell you the value in a moment. Yes, eta is a value of 1 in the UK. So you'll see that there's these formula here within the code. You won't see these diagrams, but this is where these come from. Like these are equations 319. 319 to 322, which is round about to page 36 of the Eurocode. So these are like assumptions that you're supposed to sort of glean from the document yourself. For your information also, these pretty slides, they're from a piece of software called Calcrete. In the IT labs, it's a free piece of software. Like if you search for Calcrete in Google, it's about a 76 megabyte download, and it gives you some sort of extra learning on what is concrete as a material, concrete on site, and then there's a number of modules on how to design concrete. It's produced by the Concrete Centre. It's good. The only thing it doesn't do, it doesn't show you where all the information's coming from. So you'll just see these formula, and you don't know, have they made that up themselves, or is it from the Eurocode. So I'll go through and explain where some of this information is, as much as what I can. Cal Group you can't get free, no, unless anybody knows.
Can we go off the university?
Yeah, Cal Group is the one that helps with the structural mechanics. Did anyone use that at any other universities? Yeah, in the IT labs again, if you want to catch up on your structural mechanics, there's a piece of software. So again, all we're doing at the moment, we're just trying to play around with the stresses and the strains and the dimensions of the concrete beam in order to come up with formula that will help us work out the areas of steel or the moments depending on a particular dimension. You'll see that there's this formula, and this is using similar triangles. So where you have the stress and the strain, if you've got epsilon steel divided by D minus X, that equals epsilon Cu2 over X. So it's just that formula is similar triangles. And you'll find that at some point you have to find out this value of X, and you'll be able to work that out from the strain values and the value of D. So D again is from the top to the center of the bars. X is from the top to the position of the neutral axis. That's the concrete formula. Then you've got the steel formula, and that'll be just over a few pages on page 40. That's in clause 327. Again, it gives you some design assumptions. It's the same sort of thing where your FYK is the strength of the steel, the dotted line, but we apply a factor of safety, so we divide by 1.15, which is our gamma S. This gives us the solid line that we design to, and you find that we design within the elastic range, and you'll find that FYD is always 435. Right, so this is possibly over your green page. Yeah.
I have a listen to you online because say you put camera.
The video, some of the sessions.
That's not the session. I thought some people followed you up online.
Oh yeah, we have to have a go at recording some of them. Right, let me give you a little bit of hope of where we are moving towards. Right, so we've got flexure of beams, we've got 1, 2, 3, 4, 5. 5 pages over, we've got this table. Yeah, 5 pages over, we have this table. This table has a number of formulae. These nicely are steps that you go through to design a beam. What I am going to do now is just tell you again the background to where these are coming from in order to design either an over reinforced beam or a single reinforced beam. We'll see if we get the chance to do any calcs today, but if not, we'll do them next week. So one thing that I've done within this flow chart, I've put like little numbers against each formula. So when we're going through the calcs, when we are working towards number 4, you can hopefully sort of jump back and see where that came from. And you'll see that formula 2 is where we're working out the value of x. So we saw that a little bit earlier. But in the end, from these formula, by the time you've been through them, it helps you work out the areas of steel. But before we get there, we'll go through the theory. So this is a print screen from that concrete centre sheet that's going round, and it's talking about the steps that you go through. So from Eurocode Note, we determined the design life. So buildings, how long do we design buildings for? 50 years. And what about bridges? What was bridges? 100 doesn't know. 112. So you look at Eurocode Note, then you look at Eurocode 2. 1, where you're looking at the actions on the beam, and you look at the combinations of the actions, so that you looking at your unfavourable and your favourable. Then you look at the durability requirements, so that's looking at the cover. So that's and then so with the cover you check the fire resistance also. Then after that you start looking at the beam for the flexural reinforcement and the shear. So this is where we are now, and by next week we should have done like at least the spacing of bars. I think Chandler's going to be doing shear capacity with you. So we'll go through how they gather the formula for designing beams. Firstly, defining a beam. When the load is on the top, so it is important, you've got a couple of examples, example questions where the load is from underneath, and if it's pushing up, you'd have to have your steel on the top. So when you have your load being applied at the top, your main reinforcement is at the bottom. In clause 5.3.1, it starts defining what a deep beam is. So if your span is not less than 3H, then it would be considered as a deep beam. You would design them differently to what that I'm going to be showing you for beams. If your width is greater than 5 times the height, then it would be classed as a slab. And again, you'll be using some of the formula for designing with slabs, but you've got to use a different analysis. As far as I know, you might be doing like yield line analysis with Barry Walmsley in structural analysis. So we're not designing deep beams, we're not designing slabs in this. And this is just another reminder of that effective length, that when we come to work it out, you've got the clear span, and then you add either the lesser of half the thickness or half the height of the slab for this side, and then depending on what it is here, you do exactly the same. So you need to do that. The reasoning for that is that when you have your concrete beam and it's resting on a column, they are making the assumption that this corner could crack off. So therefore, you're making your span go much further. That's your effective. So that's where the theory behind why you use an effective length rather than just your length. So you need a little bit more. Dimensions: B, width; D, we've covered that. H is the overall height of the concrete beam. This is why you need to know your cover first. Once you know your cover distance, it's just a matter of D plus half the bar plus your cover can give you H. You can have beams with flanges either side, such as this. Reasons for doing that is that you're adding more concrete to the top, so you're increasing the compressive strength of the beam. If you do have like wings either side, to work out to the effective B value, you have like little formulas of what you would use to work out what that is. And there's a lot of assumptions. These are like table 3.1 on page 29, and I think we've covered them. So in the Eurocode on page 36, we have our stress block and stress strain diagram, and I believe I've put in your notes this page, which is the same thing, except it shows you more clearly the factors of safety that you apply to each of the elements. That's above the blue line. Below the blue line is each of those with the UK national annex. So Lambda is 0.8, your alpha CC. And so it's just taken, these are all the UK ones that you'll be working with. We always have a maximum strain of the concrete of 0.0035. Eta is always 1, and we only go up to the strength of C50, 60. When we come to do the design, you've got AS, which is looking at the area of the steel that's in tension. So again, when you have a beam that's being with an action on the top, it will cause tension there. So you've got tension steel, and what you'll find is that the concrete is in compression. If the concrete can't cope with the compression, you can put steel in the top to cope with the steel. It's got the same stress value whether it's in tension or in compression. Like your concrete is only like sort of 35 to 50 newtons per millimeter squared. Again, your steel, if your concrete starts failing, you've got 435. But you try not to put steel in because steel's expensive. But when we come to do the design, AS1 is the design of the steel in the bottom, and then AS2 is the design of the steel in the top. When you look through some books, sometimes you might see that this is AS, and this could be called AS dash, which looks like a 1. But different books have different ways of labelling up the document. So with these triangles and squares and force and we got formula, like I think the only formula that we'll use is moment is force times distance, and we'll also use stress is force over area. So you got your force is stress times area. So you'll see these being used to try and create a number of formulae. So again, bit of hope. We're working towards a flow chart that in the end you could forget all the theory that we've gone through today, and you could just start at box 1, and after box 1 just move to box 2, and it's just so easy. So this one has got a flow chart. When you're doing cover, there's no flow chart. You just got to read the Eurocode. The flow chart is the steps that you go through to design a beam, but there's no steps for doing cover. So this is what we're going to be looking at. Right, when we're looking at a concrete beam, we assume equilibrium, that the force in the concrete equals the force in the steel. And if we take moments around the force in the steel, can you remember when you take moments around a force, it removes it? If we take moments around the force in the steel, it removes that, and what we're left with is moments is force times distance. Our distance is this z value. Now this z, that's called the lever arm. Just write in lever arm, z. And we can work out what z is based upon the distance in between the center of the force of the concrete and the force in the steel is the depth take away half of the concrete. Now that's 0.8x, so it's d take away 0.4x. That's the value of z. If we're doing if we're trying to work out what the force in the concrete is, you've got force is stress times your area, so it's just that formula there. And if you look at the stress, so it's when you look at the stress, it's that FCD, and we've already been given a formula for FCD. Let me just jump back. FCD, based upon those factors of safety, 0.85 divided by 1.5 is 0.567, so that's where that comes from. Or if we divide, for the FYD, if we divide by 1.5, it's just the same as multiplying by 0.87. So it's in your handout. Yeah, so Z is D take away 0.4x. So it's from here up to that green line, and that half there is 0.4x.
Should it be plus, like addition? Like
nope, I'll let you work that out in your own time. It's definitely D minus 0.4x, that distance.
I mean, the
from there
S,
to there.
you should add the S to 0.4.
Yeah, you figure that out. I'll show you that at the end. So our force is stress times by the area. So the stress is this 0.567 times FCK. The area is our is the 0. So it's the amount of concrete that is in compression. So again, we only consider the area above the neutral axis, but for the UK we just consider this lambda times by the x, so it's 0.8 times by, so to work out that area, it's 0.8 times by our width b. Multiply all that out and we end up with this value here. if we take moments around the centre, you've got your force times by your distance z. That gives us equation 1. Now equation 1 is within the flow chart. With this equation 1, what that is saying is that if I know the dimensions of my beams, my beam is, and I know the distance of the steel bars within my beam, and I know what concrete I'm choosing, then I'll know what moment it can resist. So when I'm coming to design a beam, you've got the moment that's been applied via the action, and based upon these dimensions, I can work out what the moment of resistance is, like MR, based upon that formula there. It's a little bit clearer when we come to do some calcs. Taking that bottom equation 1 formula forward, what we can do is start playing around with the formula. We take out a value of, we rearrange the z to get a value of x. You'll find that you'll need the value of x within your steps. So your x is 2.5 times by d minus z. And when you rearrange this formula, you can take out a value of k. So what they've done, they've took this formula here, and then they've took out this m over fck bd squared. So that if you let k equal that,
what does the k stand for?
K will be a factor of safety. It will be a factor that will determine whether something has to be. So from K, you find it will help you determine whether it has to be singly reinforced, that's single bars in the bottom, or doubly reinforced, where you have them in both the top and the bottom. So again, once you know what the moment is, and once you know what your concrete is and the dimensions, you'll end up with a value of K. Now, what you'll find is that for the steel and the concrete that we use, that there's a set value of K, which we'll look at in a moment. So if you find out that your K value, I think it's 0.167, if you find that your K value is above that, it means that you're going to use doubly reinforced. If it's below that, you can use singly. So again, it's another formula that you will have to work out. When you take K out of this, you're left with that. And when you solve the quadratic equation, just believe me, it is correct. You can end up with another formula for just the lever arm. So Z equals this here. Now that's the formula that I use, this Z value. If you look in other books, you'll realize that there are other formula for Z. So you can say how they're slightly different, D plus 1, D plus a half. And so you can see that they're slightly different. They are all the same formula. They're just using, they're just rearranged differently. So take comfort. Yeah, the problem is that Eurocode was still kind of new, and all these academics are doing their design in their own different ways. And when they end up with their formula, they all look different, and you start getting confused. But use this one, this value of Z. Within books, you can use tables to work out Z. If you had your moment that's been applied in the concrete, you could get a value of K. From this K, you go up to your to your line and then go across, and you end up with a like it could be 0.9 equals z over d. So you can work out the value of z from a chart like this. However, this chart, you've got to make sure that there isn't some conditions on it. This chart is based upon there being moment redistribution. We do not use this chart. So if you get the book Moseley, which is the book that I used, reinforced concrete, you'll find that there's this chart. Don't use this. It's about beams with moment redistribution. We'll do that in structural analysis. So all of that formula so far is if we take moments around the bottom. So all of it was based upon the area of the concrete. These next so many slides is if we took moments around the force in the concrete, we'll end up with formula with the steel within it. So taking moments around the concrete, we've got force in the steel times by that lever arm Z. So we've got our force again is the stress times by the area of steel times by Z. Rearranging it, we have a fifth equation. This equation is very useful for if you know a moment being applied onto the beam, you know the concrete, and you know the distance of your steel in your concrete. That will give you the area of steel that you need within your beam.
AS stands for again?
AS is the area of the steel. So if we worked out, if we had a moment and knew what the concrete was, so it was 35, and we knew the dimensions Z, we might find out that the area of steel could be 4590 millimeter squared. From that, you can choose some bars that are above 4590 millimeter squared. Just for interest, that's the Eurocode. AS is M over 0.87. For the British Standard, AS used to be M over 0.95 FYK times by Z. So based upon that we've got a smaller number on the bottom, 0.87, in the designs using Eurocode, we now use 9% more steel in our concrete design compared to when we used to use British Standard, which might upset some people. So that there is British Standard 8110, that's the concrete code. Right, I talked about this value of K, and when you have steel at the bottom, you've got this Z value. As soon as you start adding bars in the top, we have FC, a force to consider, and an FS to consider. As soon as we add some more bars in, we have another force, FS2, to consider. It's more playing around with the dimensions. I will skip through this much faster. When you consider the force in the steel in the top, FS2, or the force of the steel in compression, then you get again your stress times by your area, and you end up with another bunch of equations for over stressed beams. The way that we design it to explain just this bit here. The way that we design singly or doubly is that we work out what the moment is that's being applied. That's M. And then what we do in terms of the resistance, we find out how much moment your concrete with a singly can resist, and the extra moment that it can't resist, we design these bars to take up the rest of that moment, and that's classed as M dash.
Oh,
So again, you've got your applied moment. The way that it works is that we work out the moment that a single reinforced beam can take. So if that's 100, and you find out that a single reinforced beam could only take 80, it means that these bars then have to take 20 or above. That's the way that works out. And you've got some formula for working out the area of the different bars and the moments that these can each take.
Darren,
Yeah.
the M2, what it stands for? Is it for the moment reaction? Or it
It's M2 is how much the bars can take. Well, when we get into an example, hopefully it'll be a little bit clearer. I'm conscious that we have a lot of letters but the nice thing is that we end up with a load of formula. So they are all the formula that you need to design a beam. After that, there are a load of checks that you've got to do. So we're on the bottom of page 8. Yeah, so this is like the last bit before we sort of get into a little bit of a calc. I feel like I've killed you off. I'm dead.
Page 9. Yes, you did.
I told you at the beginning, the only thing I did, I just forgot to bring some sweets. Normally halfway through I just like hand them out, just like need like a sugar rush. It's a dry, but it's alright. I know it's a dry, boring subject. Once you've done your design, so what we have is our cover, and you will have at the end of that your area of your steel at the top and bottom, the area of concrete. Then you've got some checks. Some of the checks that you would do is you'd look at the minimum area of steel, and that's based upon 0.26 times by FCTM. That's from that table 3.1. But you find that you've got a formula, but then sometimes it'll say but not less than, so you've actually got to do 2 formulas to work out your minimum amount of steel. And somewhere it says maximum.
Max.
The maximum area of steel, again you've got to look in the national annex, but the recommended value is 4% of the concrete. So if you can't put too much steel in. So as soon as you find that your steel is greater than 4% of the concrete, you either have to reduce your steel or increase the amount of concrete.
Is that
when we designed the cover, we had steel in it. Now we're redesigning the steel. So how do you start?
You start by designing. In the British Standard, you used to do the cover last. The reason that you do the cover first is if we've got a beam, we need to know this value D. To find that value D, you've got to know your cover in half the bar. That will help you find the value of D.
Because the bar radius can change the field.
Yeah. What you can do, you can assume at the beginning. You can say, I'm going to make my cover 50, and then do your design, assuming that your cover will work. And so if you make that 50, then you know that you know that D straight away, and then do your design. If you find that your moment's okay and your shear's okay and your deflection, then you can then check the cover afterwards. So it doesn't really matter. But if your cover doesn't work, it might mean that you have to do all your calcs again. So we have to do these calcs. When you've done a lot of them, you can usually make assumptions. So do your cover first. Well, you have to. You can only calculate your cover by assuming also
So you
your
make
bar.
an assumption on the bar.
You make your assumption on your bar sizes.
Calculate the cover, prove the bar work.
Yeah. So it's like one or the other. But what they find is that the easiest thing to do is work out your cover first. Yeah. Yeah. That's right. Yeah. So that's why I give you the assumptions where there's all of these bars. And you've got some examples in the code that you can refer to.
Can I ask a question?
You can ask a question.
Yeah, mainly it's not about the calculation. What happens if you have a lot of too much steel in the concrete? What happens?
It's how it won't bind. If you have too much steel, you can end up with that aggregate. What you find is that your steel has to be spaced correctly, so that when you put your aggregate in, it goes in between the bars.
Yeah.
There's all different rules to make sure. Yeah, but you can have too much steel in.
So
Again? Yeah, if you want to do that as a final year project. So all of that 1.5 hours gets us to this chart, and I would ask you to use this one rather than the concrete centre one, just because when it comes to marking it, I'll be marking you against this. The first. I used the Moseley book, and I used the Moseley book to do that. Yeah, there is a book by Perkis, which I think is like an online version. He uses a different technique. If you want to, if you really want to get into concrete, read a few different versions of how they're approaching it. Like the concrete centre guides, a lot of people will be using them, but they're different to the Moseley formula. And I went with the Moseley ones because when I went on a course, like an industrial course, they referred to that. But it doesn't really matter which one you use. So all of that hour and a half brings us to this flow chart. What we do is that we find out what is the moment that's been applied. So this here, that's the first thing. When we've got that, we have to assume a breadth and a depth and a concrete type. So say it was a C35. When you do that, you'll end up with the value of K. If your K is greater than 0. So you've got this K, well they call it K dash, 167. If your K value is greater than 0.167, then based upon all of those dimensions you will have to have steel in the bottom and the top. So you can start the second question. If your K is under K dash,